The first video Mr. Byrne made, this template here goes with that. So I want this template completed for the first video. For the second and third video, this template works quite nicely. So you'll have to copy this twice, one for the second video, one for the third video. So in total, you will have 3 of these templates corresponding to the 3 videos. For each collision, I would like you to fill out this table. So fill out the initial momentum for mass 1, for mass 2, mass 3, and the mass 2, and then the total momentum, and so on and so on. So you'll fill out all the values here. First collision, second collision, third collision. So 3 tables of results for each one. Now at the end, there's a gap here. You can make a statement just here if you want, whether to say momentum is conserved or not. You can do it on a separate piece of paper. It's up to you. You can write here a statement if vertical momentum is conserved or not, or again on a separate piece of paper. Now this I would like from all of you as well is for each collision, I would like you to create a scale very similar to this with your error bars on and discuss based on the uncertainties within your experiment. Is momentum conserved? Is kinetic energy conserved? And what are the implications thereon? So if we look at this example, we have momentum before and after overlapping in terms of their errors, suggesting that horizontal momentum is conserved within experimental uncertainty. Here, we know that the total vertical momentum was 0 for the first video, but we seem to get some sort of vertical momentum here on someone's results. So based on that, we could say that the momentum in the vertical direction is not conserved. Here, we can say that within experimental uncertainty, the kinetic energy is conserved, but there is a chance that it is not either. So because it's within experimental uncertainty that these values are very similar, we could make the claim that kinetic energy is conserved. Now, in addition to this, what I would like you to do is explain to me step by step. So you can pick this box, for example, or whatever box, maybe that one, and so on. Explain to me how you got the uncertainty in the time. I've gone over on a document how I've done that. Okay, and I've tailored that document to this core practical. Similarly, tell me how you worked out the distance from there to there based on the video, and what kind of uncertainties are you going to associate with that distance? Are you going to say that it's uncertain based on half the radius of the ball, the full diameter of the ball? Maybe you couldn't see the small squares on the grid paper that Mr. Byrne was using, so that you could add a little bit more uncertainty onto your values based on that. Now, you give me a commentary on why you decided what you have done. I've given you something similar on my document, so you can choose to follow something similar. It's up to you. Now, I want you to explain to me how we work out this uncertainty in velocity, how we work out the uncertainty on this momentum, and how we work out this uncertainty on kinetic energy. So you are explaining to me the process step by step of how we work out these uncertainties. In the process, you need to talk about that formula you're using for, let's say, velocity, the formula you're using for momentum, formula you're using for kinetic energy. Don't skip any steps. Now, once you've explained that, you don't need to explain time, distance, velocity, and momentum again for every single one because the process is exactly the same. That's just repeating yourself. So you don't need to show the working out. Just give me the answer. The working out is not required in your final submission. However, to find the total momentum, let's say in the x direction after the collision, you've got momentum here and you've got momentum here. To get the total momentum, you just add the two up. But with the uncertainties, remember, you need to find the actual uncertainty here and the actual uncertainty here, not as a percentage, but as a value, and then add those up. And I want you to explain that to me step by step, what you've done, how you've done it. Okay? Equally, I want you to pick a total kinetic energy. So if you wanted to work out the total kinetic energy, we would add the kinetic energy of ball 1, add the kinetic energy of ball 2, get the total kinetic energy, and we put the result in the table. But how do I go using these uncertainties again? I'm not using percentages because we're adding, we use the actual uncertainties. I want you to explain that for the total kinetic energy. Now you just need to pick one part. Don't do the explanation for total kinetic energy for all parts. It's the same thing over and over again. Okay, but I want that in your explanation when you make your submission. Overall, once you've got, let's say, this picture here, it will become clearer of how you are going to come up with a conclusion whether momentum is conserved or not. And then you are going to discuss any problems with the experiment, how you could improve it, any missing physics that's involved as part of your evaluation right at the end. So there is one massive factor that we have not considered as missing physics. The ball is turning, it's rotating. We have not considered rotational kinetic energy. We have not considered angular momentum. So the angular momentum could be split into x and y's as well. There's a big piece of the puzzle there missing already. And the kinetic energy factor in terms of rotational kinetic energy, remember the ball is moving, but is also rotating. So there's translational kinetic energy in the x and y plane, but there's also rotational kinetic energy, which we have not accounted for. So maybe you want to discuss that. Some of you might just want to say we haven't considered rotational kinetic energy, but many of you are pushing for an A star. So this is where I want you to actually find out what is rotational kinetic energy. Find an expression. How would we include it for the conservation of kinetic energy? What is angular momentum? How do we include that in the conservation of angular momentum? Now, you're not going to do any experiment on this, but you could give a good analysis on the gaps. In addition, you could talk about friction. The fact that for momentum to be conserved, there must be no external forces, i.e. there's no slowing down of the ball's before they collide, and afterwards they are not slowing down continuously. So those are things that we could discuss as well. So these all combined will make up your core prac. I would like you to submit this in one go rather than in chunks. Okay? And if you have any questions, please let me know.